All right, so let's take a look at the shell sort. Um, so if we consider the pieces of the shell sort, if we look at this top while loop, well, we're going through something, the length divided by three. It's a while loop instead of a for loop, but it's still the same net effect. It's essentially acting as a fancy for loop at this point, or a simplified for loop, or however you want to look at it. But that's order n-ish. Like so, probably n over three is a little bit more exactly what's going on because it goes 1/3 of the length, but it does scale based off of the length. So something that's 1,000 versus 100 is going to be 10 times bigger, even though it's divided by three. Um, Again, another while loop. This one's kind of order n-ish. And then inside of here is another for loop, which is kind of order n-ish. And then I got another one that seems to be kind of order n-ish. So is this a cube? Like, is this, n times n times n? Well, no, it doesn't actually turn out to be that way. As we saw, the shell sort isn't slower than the bubble sort, but it still has all these extra looping going on. So I wanted to show you this example as kind of a warning of oversimplifying to say anytime I see nested loops, automatically I must be order n squared or n cubed, growing very big. We have to do a little bit of better analysis inside of here. Now, I could say, well, this thing is order n plus order n cubed or something like that, because you have an order n followed by this other one. As I said, when we're doing this analysis, we actually just ignore the order n. When it's kind of like saying, I'm going to take a 1 block walk to get in my car to drive 100 miles. Nobody cares about the 1 block walk to get in your car. They care about the 100 miles you drove. That's the interesting part of it. So the other side of it, though, is we actually are not order n cubed. We have to do deeper analysis. We have to do this much more carefully and look at what the algorithm is doing and how it's actually segmenting the data. When is it short circuiting out of this loop, and under which conditions is this happening? So we do, when we do this type of algorithm analysis, need to consider the pieces, but we can't just consider them blindly and off of some simple heuristics. So if we look at this, we actually see, and if you remember this shell sort wraps around an insertion sort. So you might be tempted to say, well, this is going to be order n squared then. But the way the algorithm works is we're essentially trying to take advantage of the law of small numbers. That when we get a when we get the partially sorted list and we use that in small numbers, we don't necessarily have the very big slowdown of the big numbers. So if we can, instead of using an insertion sort on a big data item, if we can use a series of insertion sorts on small data items that are partially sorted already, instead of being closer to the n squared performance, we can get closer to the linear performance of the algorithm. Now we can't get to linear performance. We can't already have everything be sorted all the time, but instead of sorting everything the hard way, we can sort smaller lists quickly and get to this logarithmic performance of that. And so if you do all the analysis of the shell sort, and I'm certainly not going to make you do that in this class, so we're still very much pragmatic, introductory level, but you can go look this up. The shell sort scale is thought to be log n over the log n squared times n for the omega performance inside of here. So that's pretty nice, actually. So there is a square inside of here, but it's log n squared. Log n over log n squared. But it's certainly way faster than n squared. So if I take the idea of the log, if I have a million data items, I'm not actually doing a million. I'm doing the log of a million, which is more like, what, 9? So 9 squared times a million is 9 million, but it's not like a million squared, which is, all of a sudden, that's 10 to the 12th, like, much, much, much bigger number of operations. So this is a really great way of doing that. And what the shell sort, and the reason why I'm showing you this one here is doing, is it's taking advantage of the best case scenario of the insertion sort, and it's tweaking the probability of reaching that best case scenario by creating these sublists and sorting the data. It's basically taking if you remember the insertion sort, the shell sort, excuse me, it's instead of looking at a list in order, it's looking at them every segmented section of the bigger list. So I don't look at items 1 through 5 together. I look at items 1, 50, 500, and then I move all the small ones to the left, all the big ones to the right, and then when I get down to the point of looking at the lists in order in the smaller list, they're more likely to be sorted already. I'm not moving things as far. It's a very, very clever algorithm to be able to tweak the the probabilities of having previously sorted lists and sorting those quickly to make the insertion sort more effective. So let's flip the script and look at the quicksort as an alternative, as a recursive analysis of doing this. So the quicksort here, I think this is the Java code implementation, but it's similar in C. I like the way that the Java code copies over and gives me the formatting still. But here, regardless of what the language is, we can figure out the analysis of the full algorithm by computing the time it takes to do the pivot and the time that it computes to do the partition. And then we're recursively going to do that, which the recursive analysis also gets added into this. But the recursive analysis typically ends up being a logarithmic analysis because I'm cutting the list in half every time. So we're really doing a log n over this. So we can compute each of the times and throw that together with a log n. So if we consider the pivot, finding the pivot is a constant. The start plus the end divided by 2, the middle one inside of here. There's other pivot. I can do the first one, I can do the last one. In this case, I'm doing the middle one. So it's a constant analysis though. So essentially finding the pivot is free compared to everything else that we have going on. The partition analysis, though, looks kind of complicated. We have this order n loop around it all. So we go from left to right, which again, the first left and right is 0 to n. So that's a really big stream. So the worst case scenario n, and then we have another series of order n's inside of that. But again, the worst case scenario is n squared here. The best case scenario should be something quicker than that. So the question is, does that mean the quicksort becomes n squared straight away? Because we have order n squared is the worst case of partitioning that. So if I have to go all the way from the first to the last item on either of these, because the left goes to right, right goes to left, if I pick my pivot poorly, then all of a sudden for every left and right, I'm going to be picking a pivot going through every single item. That's bad. So the worst case scenario of a quicksort actually is a previously sorted list. And so if we pick our pivot at the beginning or end, then literally we are going through 1 through 10 in this case the whole time, and then essentially resorting the data, moving the pivot, moving it around, and redoing that over and over again. So we end up with a n squared operation. So the quicksort can be very, very, very slow in the occurrences where I have an already sorted list. The quicksort is useful though, because how often do I already have a list sorted? How often does randomized data coming into me come in previously sorted? So if I can avoid the situation where my list is already sorted, the speed of the quicksort goes up dramatically. Now, in doing the homework, many of you have already realized that the quicksort, if you ran the tests as it is, if you don't add the shuffle method that I provided for you, it'll actually blow up. And we're going to talk about that a little bit more in a second. But that's because you're hitting this n squared behavior. But overall, it tends to be happening much quicker. The shuffle method I gave to you goes through half of the list, and it shuffles values for half the list by just randomly picking a number and swapping it with another one. So I'm adding in an n over 2, an order n slowdown over the n log n quicksort behavior, which is essentially you essentially can't see it until you get to really big numbers, as we saw earlier, a million of them. And again, it only happens in those really weird cases where I give you an already sorted list. So the best and the nominal cases for the quicksort are really, really quick. It's when I have fully taken advantage of this partition, and I can, essentially take the data and split it perfectly in half like I would with a tree. Again, a tree is not always, I mean, it's not the only thing that does log n here, but it's a nice representation. But if you think of it, if I have a pivot where I have perfectly half the data, sorry, a pivot, I have perfectly half the data on the left, I have perfectly half the data on the right, it becomes a really great data structure for me to split this in and get that log behavior. So again, it's recursive. So if I have a good pivot and a good pivot and a good pivot, I'm always dealing with half the data. I never have to do more than one. So I have an order n on any given level of doing the analysis, and then I have an order log n for dealing with the pivot and the partitions, which gets me my n log n behavior. When it falls apart is when I don't get the order log n, on the height. If I pick a pivot that's all the way at one extreme, so if I have numbers 1 through 10, I pick a pivot of 2 or 9 or 1 or 10, then my order log n division doesn't work out as well. When I pick 4, 5, or 6 as my pivot, I tend to be able to split my data in half and do very nicely with that. So that's the mathematical analysis. That's the mathematical analysis that tells us, okay, well, which one likely is going to be the quicker algorithms, all things being equal. But in reality, all things are rarely equal. Quicksort gets us our n log n behavior by leveraging recursion. It divides and conquers into smaller pieces, and it deals with small data to be able to get that quick response to each of that. It has a critical failing, though, that again, when we talked about when the pivots are poorly uh, derived, particularly when the data is split, I end up with the exponential behavior, not exponential, excuse me, that quadratic behavior. I end up with the n squared behavior, and I have to go through everything twice. But I can shuffle it and add a little bit of overhead to get there in situations where I do risk having already sorted data coming in. So when would the data already be sorted? Well, let's say I have a partner who's sending me data, and some clever software engineer on their side said, well, let me help them out and sort that for them. Well, they might not realize they're not really helping me out. Sending in random's perfectly fine. I'm going to sort it anyway. So that, again, pretty rare. For the most part, if you just have people randomly hitting your website, it's not going to have all the Adams come before all the Joneses come before all the whatever, alphabetically the last names coming in. So the problem with the quicksort, as you saw, is when I get into that n squared behavior on really long lists, in systems that use a stack, especially if they have limited memory, I might actually blow that stack. So it might be worse than just performing slowly. I might not be able to perform the full algorithm at all because I run out of stack space beforehand. That's the thing about recursive algorithms. So the shell sort by flip is not recursive. It's iterative. So it doesn't require you to use the stack. It doesn't call itself. It just keeps looping through the data. The biggest downfall of the shell sort is because it's jumping around this big data structure, it doesn't make the best use of what's called the processor cache. So this is a systems programming question, but your processor can load up data and make it local in quick memory and not have to page through it and whatnot. And so it can actually access small data quicker. So the quick sort in systems with that support is much, much quicker. So what tends to happen is in big operating systems, big computers, mainframes, whatnot, the quicksort is a better algorithm because it's got plenty of data. It's unlikely you're going to hit unsorted data already, and you can run it. But in embedded systems where we often try and avoid recursive algorithms, the shell sort is typically used because it doesn't require you to have a lot of stack space, and you don't have that risk of actually, essentially blowing up your process by running out of that stack space. All right, so there's a little bit of some examples of practical as well as asymptotic analysis of algorithms. I'm not going to ask you to do a ton of this through this class, but you should be aware of it because it'll come up in other classes as you get more into theoretical computer science.